Alrighty, time to start talking about refraction. And what is it exactly? Well, refraction of any waves is basically the change in speed that a wave experiences as a result of entering a different kind of medium. So in this case, oftentimes, almost always, the direction of the light or wave, other wave, changes as well because of the change in speed. But not always. There's one special case when the direction does not change. But we'll get to that. Okay, so here's our topics for this: transparent blocks, apparent depth, and refractive index. Okay, so this is a light ray, laser beam, that's traveling through a glass block, like so. Alright, if we were to draw in a normal line, let's see if I can manage that, right here, perpendicular to the surface, you'll notice that the angle outside the glass block is smaller than the angle inside, larger, wow. The angle inside the glass block is smaller and the angle outside the glass block is larger. So the angle in the less dense medium, in this case air, is larger than the angle in the more dense medium, the glass. Interestingly, if we do the same thing over here, bam. Anyway, those are roughly drawn. You'll notice, hopefully, that the line here, bam, this angle is equal to that angle. The line here is parallel to this one. Because the sides of the glass block are parallel, the refraction happens exactly the same in both cases, just in reverse. So you come out the same angle you entered, but with the light beam offset from its initial starting path, but parallel. Alright, that's what happens with a parallel-sided glass block. Here you can see in diagram form what happens in the air, which is less dense. Bam, you have that angle. In water, more dense, angle gets smaller. Notice it's coming in not at the normal line. I'll talk about that more in a bit. But coming in at some angle, changing to a smaller angle with the normal line. Alright, so the principle there, when light refracts, the smaller angle is always in the denser medium. In this case glass, in this case water. Okay, so let's define terms. The angle of incidence is the angle at which the light ray strikes a boundary between two optically transparent media. So first medium, air, second medium, water, boundary between them, the angle at which the light ray strikes the boundary. That's the angle of incidence. Angle of refraction is the angle taken by the light ray after it passes through the boundary. So bam, hits the boundary, passes through, changes its angle. Alright, and there's the new angle. That's the angle of refraction. Alright, pretty simple, pretty straightforward. We'll move on to the next slide. Alright, really fun one here, apparent depth. This is the optical illusion in which it appears water appears to be shallower than it is, right? Or in which straight objects appear to bend when they enter water. It's the same phenomenon, just a different form of it. So here's a straight pole. Looks like it bends. We know it doesn't bend, right? It's actually straight. If you could pull it up out of here, it would be a straight pole. So why does it look like it bent? Well, basically here's what happens. This is like a diagram of a pencil sitting in a tub of liquid. This is what the pencil actually looks like if you could see it without the water there. But because the light rays refract, they bend away from the normal line when they leave the more dense medium, right? Because the angle is bigger in the less dense medium. Water is more dense. So the light rays bend away from the normal line. Then what you see appears to be over here at position Y. What actually is occupying position X appears to be occupying position Y. Notice that it's shallower than X. It looks like it's shallower than it actually is. It also ends up making the pencil look bent. Now here's one to really blow your mind. Alright, take a look at this pool. This is a drained pool here at our school. Alright, it was drained. Totally drained. This is what the pool looks like when it's empty. Totally cool, right? Notice the top of the wall here, bottom of the wall here. right? And the water line would be right about there, if there's water in here. Notice how far apart these colored lines are? Alright, here we have a picture. A little bit of glare on this picture, so it's going to be kind of hard to see. But here it is with water. Notice, those are the same colored lines. The same colored lines. Same ones as that right there. Dude, what? That is crazy. Look how shallow that looks. That's nuts. Alright, and then here, you can see this is the apparent depth. I can't really tell where the bottom is, but it's somewhere in this region. There's too much glare on the pool right there. But right around in here. Anyway, the point is, you can see clearly the pool appears a lot shallower than it actually is right there. Black lines. Alright. That is, in my mind, amazing. This is what happens when light refracts, and the steeper the angle, the bigger the angle from the normal that you're looking. So this would be a pretty large angle if you imagine a perpendicular line coming up out of the pool, and then measure the angle of this light that's coming toward us. It would be a big angle with the normal line. So the bigger the angle with the normal, like this, if you look over here, the bigger this angle is, the bigger that angle, the more the light refracts, the shallower the water looks. Okay, which brings us to our point. Well, one of our points. We've already made many points, but this is the equation that we use to describe refraction of light in various media, and that is refractive index, which we represent with a little n. Alright, so the refractive index is equal to sine of angle I divided by sine of angle R. There's an important thing that I'll have to mention here in a second, but basically this is a unitless number. There are no units to remember. You just write down the number. So for example, water might be about 1.3. So anyways, important point, really important point. Angle I does not necessarily mean angle of incidence in this case. It's kind of confusing that way, but you have to remember angle I just is going to be whichever is the angle in the less dense medium. Alright, the less dense medium. Angle I, less dense. Angle R, denser. More dense. So angle R is in the denser medium. Angle I is in the less dense medium. Usually you talk about light coming in, like incident on the surface of the water, and then it bends. So that makes sense. But sometimes you talk about light coming out from the water, and then the light ray is incident, right? The one part that's in the water is actually the incident ray. But if you do it that way, it messes up the refractive index number. It ends up backwards. So just remember, angle I is less dense, angle R is denser. Alright? Alright, and then one more form of this equation is in reference to speed of an object, or of light. So you can actually use the refractive index to calculate the speed of the light. If you know the speed in one of the media and you know the refractive index, then you can calculate the speed in the other one. Or if you know the speed in both of the media, you can use that to calculate the refractive index. So this basically is a way, it shows that the refractive index also describes the relative speeds. So the speed of the light in the various media can be compared by comparing their refractive index. The bigger the refractive index, the slower the light travels in that medium. So basically, if this is bigger, that means slower. Alright, that's all for this video. Hope it was helpful. Thanks for watching, and we'll see you next time.